So this is Unit 1, Lesson 1. The unit is called Limits and Continuity. The lesson is Can Change Occur in an Instant? And this is the first lesson in our AP Calculus course. Let's take a look. So what we're going to learn in this video is what is a limit? Where else would I have heard of limits? What does a limit mean specifically in math? So what is a limit? So we've used limits all the time. When you want to buy something online that has a good discount, sometimes they give you a limit to how many you can buy. So in this case, the minimum purchase quantity for a product is 5, so that's a limit of how low you can go. A speed limit sign, 120 kilometers per hour, is kind of is how high you can go. What's the upper limit? And then just kind of a more abstract idea. And if you haven't watched this movie yet, stop watching this video and go watch Moana. But how far you go is basically the question of what is the limit. So what about math? So in calculus, a limit refers to the value of a function is approaching. Let me say it again. A limit refers to what value a function is approaching as the independent variable, or the x value, approaches a specific value. So in algebra, we talk about finding or evaluating functions at a specific point. Whereas in calculus, now we're going to talk about finding the limit as x approaches that value. And so those are two different things. And so we're going to unpack that in this lesson. Let's look at an example. So here's a graph of a y cubed function. And we're looking at the value x equals 1. And I want to find what's the instantaneous rate of change for this point. We have two lines on this graph at x equals 1 and x equals 1.2. And we want to find as this second point, 1.2, as that point gets smaller, 1.2, 1.1, as it gets closer to 1, but not actually at 1, what's going to be the slope of this secant line? And so we're going to find the limit here. So in this case, the limit of the slope, we know our slope formula, so we have the change in f of a minus the change in 1 divided by the change in a minus 1. And so for these points, x equals 1 to x equals 1.2, and this interval, we're going to get a secant line with a slope of 1.195. So now if we look a little bit closer, so instead of before we were looking at from 1 to 1.2, what if we look at 1 to 1.1? It's half the interval, and so we're going to get a secant line with a tighter slope. So if we look at this thing, we're going to get f of 1.1 is going to be 1.536. And so if we look at the rate of change, or the slope, we get a slope of 1.36 on this secant line. And so we're talking about limits here as this x value approaches 1, not equal to 1, but as it approaches 1, what's going to be the limit of our slope? How high is this going to go? So let's take a look. So here's a graph we can play with. It's got our slope formula, it's got our slope. We've got the equation for our secant line. We've got the equation for the cuboid that we're graphing, or the x cubed function. And we're just going to take a, and we're going to make it arbitrarily close. So if 1.2 is a, we get a slope of 1.196. If a is 1.1, we get a slope of 1.39 or 1.36. About 1.05, we see our slope's going to get higher. If I go 1.005, it's higher but not as much higher. It's still 1.493. If I add another 0, 1.499, keep adding zeros, I'm going to see that our slope is kind of reaching its limit. So in this case, we're approaching a slope of 1.5. And now, because this is a computer program, we're going to have a rounding error eventually. And we're going to jump above 5. Boom, there it is. And so that's only happening because our computer is going to round this answer and give us something close. But as you can see, if we add another 0, we're back below 1.5. Thought we were going to get higher. Nope. We're going to stick around 1.5. And no matter how many zeros we add, we're just going to find that our slope has a limit of 1.5. So here's that table kind of worked out. And to be clear, we haven't confirmed or proven that the limit of that secant line slope was 1.5, but based off of the graph and based off of the table, we can pretty strongly estimate that the limit of that slope is going to be 1.5. Um, for a more in-depth look at finding limits from tables, we'll unpack that in future lessons, and then even later down the road, we'll figure out how to confirm the limit is 1.5. But at this point, we're just kind of estimating. Let's talk about um, the takeaways. So why do we need to use limits? Because rate of change at a specific point, or the instantaneous rate of change, can be hard to calculate. If we try to find um, the change in distance over change in time at the same point, in other words, if we go from f of a to f of a over a minus a, then we kind of run into the trouble of we get 0 over 0 for a slope. And that doesn't make any sense. If a exactly equals 1, the problem is we have f of 1 minus f of 1 over 1 minus 1. And that's going to give us an undefined slope. So that doesn't really help us at all. So we're talking about instantaneous rate of change. We're going to be looking at what's called limits. And limits are going to help us find those numbers without getting into trouble, as we call it. We're dividing by 0. And so this is kind of highlighting that thing that I said right there. So if we're looking at the same value b, and the intervals from b to b, we're going to find f of b minus f of b over b minus b, or change in y minus change in x. And that yields us an answer of 0 over 0. And that doesn't help us at all. So we're using this concept of limits to figure out as the interval approaches 0, or as a approaches b, what is going to be our slope value. And we're going to call that instantaneous rate of change. So who cares about instantaneous rate of change? Instantaneous rate of change is used all over the place. In calculus, and then if you get to physics, you're going to spend a ton of time talking about velocity or speed, which is change in position over change in time, and a lot about acceleration and how those are related. Gosh, all of these things we could talk about for a while. The let's say like population, if you know your current population, the instantaneous rate of change at any given point, then what that does for you is it helps you predict what the next year's population is going to look like. Or if you have the marginal cost of if you're producing something, if you produce 500 things and you know the instantaneous rate of change at that 500th thing, then you can predict how much, what the cost will be, the incremental cost of that 501st thing. So instantaneous rate of change can help predict the future in some sense. It tells us if a value is going up or down or what and how much. So many ways it applies. So let's look at a couple examples like we'll see on a question for a quiz. So the spread of a rumor is modeled by the function r of t equals this right here. So r of t is the number of people that have heard the rumor, and t is the number of days since the rumor has started. So t goes from 0 to 30, so that means we're looking at 30 days. R of t is how many people have heard the rumor. So we'll look at this curve right here. And I got some scribbles on here, so I apologize. And so at the value t equals 4, the instantaneous rate of change is modeled by the slope of this tangent line. This tangent line that intersects r of t at exactly 1 point when t equals 4. And so what we're going to do is we're going to find an estimate for the instantaneous rate of change for r at t equals 4. So if we look at this as a multiple choice question, um, we're trying to find, okay, so we have 4 examples or 4 options. A doesn't make any sense. A is not a limit kind of a question. It's going to be, it's not even a slope. It's just a value at r equals 4 or t equals 4. So looking at B, C, and D, if I look at B, we're looking at t equals 1 to t equals 4. So we got a point below on the graph to t equals 4. So we kind of have this line right here that kind of gives us an estimate of what that slope's going to be. If we look at C, C is looking at a slope of a line that joins 4 to 8 in this interval from 4 to 8 on the curve. R of 4 is here, 8 of 4 is up here, and so we get another line that doesn't quite give us a tangent, but it's an estimate. D is going to be the best choice. And the reason that is because to find the best estimate, we want to get the closest interval possible around the point t equals 4. And so 3.8 to 4.2 is the tightest interval around this point. And so that's going to be our best choice. So the same question, if it was a multiple choice question, it would look something like this, and you want to find that closest interval. If it was a free response question, it would define for you, kind of how they want you to write it. So approximate the instantaneous rate of change of r at t equals 4 using t equals 3.9 and t equals 4.1. Interpret this rate in a context of this problem. So we would look at f of 4.1 minus f of 3.9 divided by 4.1 minus 3.9. And that kind of setup would be a reasonable estimate using the right notation. You wouldn't have to calculate that at all, but just that's what it would look like. Another multiple choice question. So a ball is rolling down a straight path, and its position is modeled by the function b of t, where b is the feet from the starting point and t is the seconds since the ball started rolling. So basically we have a ball that's been rolling for 25 seconds, and we're figuring out what's its position at any given point. And so similar to the last question, we're going to want to find what is the best estimate of the velocity of the ball in feet per second at time t equals 12.5. So that the best answer we want to find is the tightest interval around 12.5 that we can find. So we look at A, B, and C, and D. A is not even an interval question, it's just an evaluation. Or it's not a slope formula, in other words. If we look at B is going to be our tightest interval around 12.5. So we go from interval of 12 to 13. We can yield this will be a very tight estimate. 9 to 16 is a wider interval, so that's not going to be our choice, and definitely not D. 0 to 25 is not going to be very helpful. So B would be the best answer here because it's the tightest interval around t equals 12.5. So next example, a bicycle is being ridden down a straight path and its position is modeled by the function b of t, where b is the starting point and t is the minutes since the bicycle started traveling from 0 to 20. So the bicycle is traveling for 20 seconds. This graph models its position as in its distance from the starting point. So we have that first 6 seconds we're traveling at a constant speed away, and then from 6 to 8 seconds the bicycle is not moving. His position is not changing because that guy's not moving. And then from 8 seconds to 17 seconds, he's moving again, but we have a steeper line, so we know he's moving much faster than he did in the beginning. After 17 to 19 seconds, we see that he stopped again, and then we have a very steep line going back to 0 from 19 to 20. So however fast he was going from 8 to 17, he's going super fast that last second. Super fast. So anyways, the question says, find the velocity of a bicycle at time t equals 7. So t equals 7 is the point right here. And so if we're looking at a very tight interval around this point, 6.9 to 7.1 or whatever. We do see this as a flat line at this point. And so a flat line definitely has a slope of 0. So 0 is going to be the best estimate on this one. You could even have a little bit wider of interval on this because it's such a straight line. But for that reason, we have a slope of 0. It's a flat line. A is our best answer. All right, that is the end of this lesson. Goodbye.